Welcome to the Rich Report, a podcast with news and information on high-performance computing. Today, my guest is Jean-Pierre. He is from Atos, and he's the CTO he's also the director for HPC at Atos. Jean-Pierre, welcome to the show.
Hello, bonjour. Hello, everyone. This is Jean-Pierre.
Well, thanks for coming on the show today. You know, Jean-Pierre, I saw your slides came up on Twitter or something, and I was wanting to learn more about your new BXI Interconnect. And it was great that we could arrange this and let other people hear your presentation and learn about this because it sounds like a very innovative technology.
Yes, thank you, Rich. I mean, it is actually. We do believe it's a very important piece of technology that we are bringing to the market with BXI. BXI stands for Bull Exascale Interconnect, and so it sets, our ambition where we want to go.
It really is what it says it is. This is intended for an exascale system somewhere in the next 5 or 10 years.
Well, I hope it's going to be earlier than 10 years. So today it's 2017, so we do expect that to be able to deploy with our customers exascale system in 2022, 2023, and maybe earlier, but it all depends on technology and budgets.
Oh, yes.
Budget's always an issue.
Yeah.
Technology we can score.
Yeah, yeah. Well, Bull and Atos have such a great long history with large scalable systems. I think this is going to be very exciting to learn about this. So, Jean-Pierre, I brought up your slides. I'm on slide 1 right now. Why don't we get started?
Okay, so I already mentioned that BXI is our new interconnect, Bull Exascale Interconnect. And if you want to move to slide number 2, I will just set the stage and explain a little bit where this fit into our roadmap. And so we came up, we started last year, 2016, and this year we bring up a completely new set of products to the market, and the architecture around different CPU architectures, so that the traditional Xeon EP, but also Xeon Phi and the GPU accelerators from NVIDIA. We're also introducing this year systems with ARM processors, and all of this is going into our new platform, Sequana, this new flexible packaging Sequana that you have a picture at the bottom. And on this platform, we're also providing a couple of interconnects. So traditionally, InfiniBand. We've been carrying InfiniBand for a long time, and so it will be available on Sequana. But most importantly, and definitely the topic of today's presentation, we'll have BXI, our new exascale interconnect that we're introducing. And all this is, orchestrated by our software suite, which we call SCS, that you have mentioned here. So this is, the product we started deploying last year, and that will complete this year. We'll have a full set. And then, when we look down the road, next year, the next 3 years, we'll have, updates of this technology. And probably the most important thing, technology improvement that we see is really a better integration of all the components, which mean that in the same, HPC node, we have a tighter integration of the compute engine, and so it's difficult now to talk about CPUs anymore with all the different kinds, but the compute part, the memory, the network, and the storage integration. And, obviously we'll improve on the packaging. And I'll mention a few words of what we're doing there with Sequana. And the energy and performance, really optimizing energy for performance and performance for energy. And this is, the next set of improvement that will be coming in the next 3 years. And after that, we will be ready for some larger exascale deployments. So if we move now to slide number 3, just to set the stage of, why, so much interest and so much focus on the interconnect. And traditionally, HPC systems are highly parallel. If there is one definition of an HPC system today, is that it is a parallel system. And if we're looking at a Petaflop system that we've been, the Petaflop class system that we've been installing in the recent years, they were featuring, thousands of CPUs. So now you can get, maybe a petaflop with fewer than 1,000 CPUs, but this was the ballpark. 1,010, 110,000 CPUs, typically x86, and some storage, multiple tiers of storage. But when we look down, what are on slide 4, what the HPC system specifically, and especially the eXascale system, will look like in the coming years, then you can see that you'll have many more nodes, compute nodes, because there is so much that you can provide, that a single node can provide. So we'll have more nodes, more parallelism. We'll certainly have more data, and the storage side will also grow quite substantially. And here I'm just focusing on the HPC. I'm not saying I'm going into the big data where this part of the storage will be increasing even more. So as we're putting, we're increasing the size of our system in terms of the number of nodes, the parallelism, we're putting even more pressure on the HPC, the interconnect. And on slide 5, if I look at the specification of the ideal HPC interconnect, first, as I said, it has to be scalable. We're moving from, and has to be efficient on size, between 100 and tens of thousands of nodes. I think it's fair to say that the eXascale system, the first eXascale system that will be deployed, will have, probably in the area of 50 to 100,000 nodes. And so this is why scalability is so important. When talking about systems that size, they have to be reliable. I mean, there is, no matter how you do and what kind of components you use, there will be some faults and and you need to override this and to make sure that your system is fault tolerant. So this goes with some redundancy, a way to to work around failures. But this is something that you have to integrate into the design of your system and specifically in the interconnect. When we're talking about HPC, high performance computing, the next thing that goes with it, and I think it's a very important point, is the high performance communication. As I said, when you have so many threads spread over the large systems that need to work tightly together, the communication becomes crucial and very important. And in order of importance, from my standpoint, the most important characteristic is probably the latency, having a very low latency. And this becomes even more crucial as the cores that are running into the different nodes are getting slower and slower to be more efficient, energy efficient. So it's a paradox here. You have to improve your latency as the core are running slower. And the message rate, since we have more and more cores and different nodes, you'll have a much higher rate of messages that are flowing into the system, and you need to handle that. And finally, bandwidth, which is probably the easiest one. I mean, one easy way to get bandwidth is to flatten the length, but it's as I said, it's probably it has to go together with an improvement in latency and the message rate. Has to be efficient, and one thing that we've seen that was a pain point for interconnects was the fact that the memory that would be used for to run your communication will grow as the system will grow, and has a number of threads in the system, especially for MPI. So having a constant small footprint is something which is very important, especially as memory becomes so important. When one characteristic of the large, the new HPC nodes is that they have very fast memory, but that memory capacity is shrinking if we compare it to some system that we've been installing over the last few years. So making sure that the memory is used efficiently is very important. Adaptive routing, when you have a large fabric, you want to make sure that you work around some congestion point, or you avoid congestion altogether. And finally, you have to be able to handle several types of data flows. Typically, you may have a lot of small messages that are generated by the MPI, communication, and in the same fabric, you may also you may have to handle at the same time big chunks of data that are moved to your storage subsystem. So all of this has to go together. And one of the things that seems important is that you don't want to do this in the CPU, because the CPU, as I said, are growing slower, and something that the hardware should handle. And this is exactly where BXI on slide number 6 comes in, and to the different problem that we try to address with BXI. It is, as I said, our first generation of interconnect, and the main feature is that it has hardware acceleration. And so that guarantees that you'll have performance, so performance being the compute performance, the CPU are freely available to do for computation, and and don't have to deal with the communication primitives. Again, we're targeting low latency, the message rate, and what we think is a good high bandwidth. The full acceleration in hardware for HPC is done through a low-level library that is Portals 4. So since we were starting, this was a new product that we're bringing to, and starting from scratch, I would say, rather than starting, on a white page, we started using a library that was being very much used for communication, Portals, which was developed mostly as Sandia. And Portals 4 is, as it says, the fourth generation, and this is where we started from. And BXI is, in a nutshell, the hardware implementation of the Portals 4 communication primitive. It's very well adapted to for MPI and PGAS kind of type of communication, and there is good support for very good support for the high performance collective operations. Get back to that again. Now this is, again, BXI is targeting large systems and has to be not only scalable but also efficient and reliable. So in terms of scalability for this first generation, we limited ourselves to a maximum of 64K nodes. Probably in the future generation we'll increase that, but already today this is this could bring us already with this size to the eXascale. Adaptive routing and quality of service is also big features of BXI, and a lot of features related to error checking and avoiding and failures and correcting errors that are either from end to end, so checking that what you receive at the end of the one end of the network hasn't been corrupted, but also at every step as you move data from one point to another in the network, so that the link level TRC, the link level retry that we put into place, and then in every little chip in the communication system. Another important point I want to make is, this is not something that we invented from nowhere. We base a lot of the design requirement on the collaboration that we're having with the CEA. So CEA is a French atomic energy institution, and it's one of our very close customer and partner. And BXI is a result of the co-design effort that we have with CEA. On slide number 7, just have a small picture to explain how we're building this, and we're basing BXI on 2 chips. On the left, you have the network adapter and chip, and so the code name for that product, for that chip, was Lutetia, and it is interfacing with the nodes through a PCI by 16 Gen 3 interface. And so that's on the top, and the bottom you see that there is one link to the network, and the BXI link is 100 gigabit per second, so it's 4-lane at 25, and it's exactly in line with what you have today for other types of interconnect, either InfiniBand EDR or OmniPass 1. And the design was on purpose to align with current top communication interconnection and so that we could reuse a lot of the technology and have an optimal price. In terms of the design goal for that network interface, we're targeting latencies less than 1 microsecond, and so that's for MPI communication, and that involves the different layers in the software stack, but also a couple hops through different switches that like the one that you have on the right. In terms of message rate, we're able to handle more than 100 million messages per second on each node. And all this, when you put, to connect all of these thousands of nodes, we're using a large switch that we also developed. This is the other ASIC that we've developed. The code name was Divio. Has 48 ports. So again, the BXI links are 100 gigabits per second, bidirectional. So that's where you get to 9600 gigabits per second of global bandwidth in that chip. And that probably is worth noticing that it's the highest bandwidth that you have available at the moment in any switch in the ASIC. The network adapter, the main, just to emphasize the main features on slide number 8. So again, it implements in hardware the purposeful communication primitives, and that allows to really efficiently overlap communication and computation by offloading all the communication primitives to the network adapter. Again, it's a very well adapted to MPI, and there is in hardware all the features that are handled for the management of all the different communications that are in the flight, and also matching at the other end of when you receive a message. The processing of that message is handled transparently by the hardware without having the CPU to be involved. Beside MPI, it's also well adapted to PGAS and the MPI one-sided, and that uses an ultra-fast path within the NIC. So, well, one thing is you shouldn't have to mention that to go that fast, to be very efficient, you need to bypass all the OS, and this is obviously done in BXI. The collective operation is something that is very interesting. Having thousands of nodes and being waiting for collective operation like an all reduce for many milliseconds sometimes is not something that's going to help your application perform well. So the feature that we implemented in hardware for BXI is that all the collective operation handled within the network, and that the CPU are not involved in this collective operation. You just set up, let's say, an all reduce operation, and then the hardware send all the messages that are necessary, and using this atomic operation that have been implemented in hardware. I already mentioned the lot of effort that we put into providing high reliability on the system, and at the NIC level, at the endpoint level, the end-to-end reliability, which is pretty standard for large HPC systems. That's where we check the integrity of the message from one end to another. Also, for specific to MPI, the ordering of the message, making sure that they arrive in the right order, and if something goes wrong, we don't receive the message in the right order, then it's you have the possibility to retransmit all the lost messages that are and the ones that have been lost, or corrupted. We're defining many different ripple channels up to 16, and so that's a way that we can avoid deadlocks in the network and optimize the resources for the different types of workflow that we may have. As mentioned already, small MPI messages, big IO transfer. And finally, something which is always very important when you look at performance are a rich set of performance counters that are available at the application level for performance analysis. In particular, in the whole network, you're able to select specifically as one type of application, one type of user, so you can really narrow down and zoom down to the whatever performance issue you may be tracking. On the BXI switch, so it's as I mentioned, it's 48 ports. So you have a floor plan picture on the right. This 48 port, 100 gigabit length. Latency is 130 nanosecond. That's pretty good. So if you have a big system with 64,000 nodes, you may not traverse more than 5 of these switches. So that's very good low latency. On the left, you have a picture of one of the instantiation of the switch. Here it is on a standalone unit that it's a 1U high and has 48 ports. So you see here from the rear of that unit, you have in the central part you may recognize with the with the heat spreader, the BXI switch in brown. On the side, you have the redundant PSUs, and around the switch itself, you see a set of little wires, blue wires that are coming out of different optical modules. And in the front, at the top end of the picture, that's where you have the 48 different ports, optical ports for this switch. So this is an example of how we use this to build very large BXI systems. Okay, so on slide 10, here is a summary of the different features of the fabric itself. As already said, the BXI can scale up to 64K nodes, and with a very high bandwidth links, 100 gigabit links, 4 lanes at 25 gigabit transfer per second. Has some very interesting feature for reliability, and where you check, end-to-end consistency of the messages, but also that the message comes in order at every link level. Good. BXI was designed to be quite flexible, and for this we have a full routing table. That full routing table is available for each input port. So if you're not a specialist, that might not mean much, but it means that you can implement BXI with any kind of topologies, not only the fat tree, which is the one that we're using on all our systems, but also traverses, flatten, butterfly, hypercube, and other things that you may invent. There are specific features for adaptive routing there, avoiding working around the congestion points. And we have quite an extensive buffering, which is available for each of the 16 virtual channels that are defined in the BXI. And so that's a way to avoid deadlock and to balance the different kind of traffic that you may have on the fabric. An important part of the management of BXI is that it's done out of band, and so that's a way to make sure that you can control all the components in your system. And on the slide 11, here are the details of the software stack suite that comes with BXI, and hardware without software is not very useful. So on the left, we have the BXI fabric management and the different components that goes, the handle performance, supervision, that's handling failures and fixing them. The topology manager, making sure that all the cables are connected to where they should be, and routing, making sure that they're forwarding all the messages from one point to the destination. On the right side, you have the user software stack, and if you look at your application that maybe has been parallelized with OpenMPI, then you shouldn't change anything. It will use a standard OpenMPI library, but on BXI you would switch to a native interface, or the native Portals 4 interface, which we developed with Sandia quite a few years ago, and it's publicly available on the source tree of OpenMPI. So your application doesn't need to be changed. We'll still use the MPI, still use the standard open MPI library. Just at runtime, it will interface with Portals 4. And as I mentioned, BXI is mostly a hardware implementation of Portals 4, so you map directly with the BXI hardware. On the right side, you have the user stack. So if you look at one application, so a user application, whatever it is, let's say a CFD application that is running on your system, if it uses MPI, say Open MPI, it will use the standard Open MPI library that you can download on the network. What will make it work well on BXI is that we've developed over quite a few years ago already a Portals 4 native interface for OpenMPI, and that flows directly down to the hardware. Since I mentioned that Portals 4 and BXI are very close together. BXI is really the Portals 4 implementation in hardware. So what you have to remember from this is that whatever your application, say an MPI application, an application using SHMAM or UPC PGAS type of programming, you won't have to change anything in your application. It will use standard library like OpenMPI or Lustre or whatever. And then we have been providing over time the Portals 4 native interface for BXI. And that's all ready and working at the moment. A few words on slide 12 about the fabric management software. I already mentioned the four important modules that deal with the routing, the supervision, that is handling the failures, the topology, which is checking that all the cables are connected to the right points, and the performance, which is something important once you want to improve your application efficiency. All of this is done out of band, meaning that the BXI Switch is managed through an external Ethernet management network, and so this way you're sure that you can control, reset, or manage your network, even though there may be some internal problem. The one thing maybe I want to have a few words here with this slide about Bull Sequana. I mentioned that we've developed and we started shipping this new platform for our high-end HPC systems, and we designed it from the beginning to be open and modular. And by this, we mentioned we want to say that it's able to host different kind of compute nodes, either using Xeon EP, Phi, NVIDIA GPUs or ARM processors, for example. And since one type might not feel fit for all type of applications. Again, since we're looking at very large installation with tens of thousands of nodes, it makes it easier if you start with a large building block. And the building block for both our platform, Bull Sequana, is a set of these 3 racks. You have a picture on the left, which embed up to 288 nodes. So if you start with a building block which is 288 nodes, with a few dozen of this, you go up to some very high performance and large systems. But one important point, and connected to our topic today, is that it's embedding different type of interconnect. So InfiniBand, as I mentioned traditionally, but also BXI, and it's fully optimized within the cell here. This 3-rack unit. You already have the pre-wired 2 levels of switches for interconnect, and you also embedding here all the service node integrations. That means storage, administration, logging, and so on. And finally, one important feature of this Bull Sequana platform is it's liquid cooled, and we can cool the whole data center with cold water, which may be at the temperature of 40 degrees Celsius. That's more than 100 degrees Fahrenheit in the US. So that is make it very efficient and for large data centers, and in terms of you can run your data center with a PUE as low as 10 something, 102, 103. One example of nodes that we are hosting in Bull Sequana, you may find on slide 14. This is a Xeon Phi, the nice landing, and you see that one of these trays, which is still called blades, even though it's a little larger than traditional blades, you have 3 nodes, and you see on the left here you have the mezzanine board, and that's the one that you can. That's where you have the network interface. So here in our case it could be BXI, and this is the node level, and then these compute blades, we put them in the front, in the back, on each side of the cell. So that's how you get up to 288 nodes. It can be very dense. It's all liquid cooled. There is no airflow in the system. So you have a picture of the 3-rack unit on the left. On the bottom, you see the logical diagram of how we interconnect the 288 nodes. You see that you have 12 switches that are connecting each of them connected each of them with 24 nodes, and it's connected with the second set of L2 switches. On the right, you see how they are wired. So this is, as I said, on the left. On the bottom was the logical. On the right is the physical implementation of this. So the nodes are connected to the L1 switch horizontally, so a small cable that you may see in the back. And in the front, the L1 switches are connected to the L2 switches that are on the top and the bottom of the central unit. And so all of this is done with copper cable in what we call a copper cable backplane. So customers don't handle this cable. They're all pre-wired into the Sequana cell, and it's copper, which means that it is not very expensive. It's quite affordable, and a very high quality signal for this size of links, which are less than 2 meters. And on slide 16, this is how we interconnect 2 examples of interconnection of different Sequana cells. On the right, you have direct connections, so that works pretty well for system size that are less than, say, 2,000 nodes. And on the left, with a full factory, you can go to tens of thousands of nodes. Finally, just I want to mention on slide 17 that BXI is alive and kicking pretty well. We had our first prototype installed back in October 2016 last year. It was a 256 node KNL, and was installed at CEA. We were able to run, obviously, as soon as it was installed, Impact, and it was on the top 500 list in November, and the Green 500 list as well. We also, but I mean, this is Impact is one thing, but our customer CEA has been using the system to run full applications, and we always see pretty good performance on this one. They are at the level, if not sometimes much better than what we have with EDR and sometimes OmniPass and OmniPass. We're waiting for the final spin of stepping of the chip of the network interface, and we start before the summer the full deployment of a system at CA, which will have more than 8,000 nodes. Finally, just a slide of conclusion on slide number 18. Just to mention that BXI, is well and alive, and we have our first prototype I just mentioned that is already installed at the customer site. We will start pretty soon to install a much larger system with the same customer, CEA, with more than 8,000 nodes, and we have more customers that are already enlisted to use BXI and this system will also be started to install in 2017 and next year as well. Ongoing is one thing to have developed all the hardware. The software is, still the software development is ongoing. Adding more feature, more tuning to all the different software components, and we're also looking at growing the BXI ecosystem. Not just working with our partner and all the software that we are designing ourselves, but also we are planning to open up BXI, which is the software part, to a larger community, and to start the Open BXI, you see the logo on the right, initiative pretty soon. Obviously, this, as I mentioned, this is our first network, BXI, the first generation. We are already planning and preparing BXI 2 and BXI 3, and just to mention where we're going, we want to integrate a much wider range of technologies beyond what is possible today with BXI. And for this, we are also looking at new usage models, and not to mention big data or machine learning as two examples of things that we're looking at. So with this, I conclude my presentation on BXI. And Rich, if you have any question, I'm ready.
Okay. Well, thank you, Jean-Pierre. First question comes to mind, and it's why wasn't InfiniBand good enough for what you wanted to do at the eXascale? What were the big gaps that you saw?
The big gaps of when we started this project is InfiniBand has been improving over time, but it was definitely a lot of it was done. We require work in the hardware.
Mm-hmm. Yeah.
So in the CPU, and you would have to rely a lot on the CPU, and especially with the many core, the GPU that we were planning. This would not do it, and so InfiniBand is catching up. They're adding more and more features, but they're not to the level of what we have available with BXI today.
Mm-hmm.
Able to handle all the communication part in hardware. They do part of it. They do some differently, but in the end, I believe that BXI is quite unique. The other point is being able to integrate. I mentioned in my introduction slide about our roadmap that the next step we're looking at is not just building the systems as we see them today, but it's also improving the architecture and looking at a much tighter integration of the different components of our systems. And since the spine of our an HPC system is interconnect, it's something that we needed to control. And so that's for us, it's a very strategic move and development that we're doing with BXI.
Well, Jean-Pierre, of course, Atos is a cloud company as well. Does BXI technology have a play there in the data center as well, do you think?
Yeah, by cloud, you mean generic data center that is used for other workloads than HPC?
Yes, absolutely. That's the question.
Right. So with this current generation, I don't think it would be very well suited. The first implementation of BXI is really targeting HPC.
Yeah.
BXI is an HPC interconnect.
Got it. Yeah.
For the time being.
Very good. Okay, and then last question is, exascale systems are, of course, many nodes, lots of racks. Does BXI have advantages for applications at the rack level? At the base Sequana system, do you think that'll have some advantages for you out there in the market?
Right, and we're always looking at the difficult thing, meaning in being able to implement many, thousands of cores
yes.
of nodes. But we're not forgetting that the big chunk of the system that we're deploying, and even the revenue, in terms of revenue, not just a number, are systems that are in the range of hundreds to 1,000 nodes. And for this set, yes, BXI is definitely work well. It will, especially with the flexibility, having 48 ports, enables you to connect a few hundred nodes with very few switches. So it has some benefits, and when you say that, it has some benefits for in terms of since you have few elements, it would be cheaper, but also in terms of its efficiency itself, since you have you need to go through fewer hops to get from one point to another.
Yeah.
So definitely we didn't we kept that into mind, not just the big ones, but also the systems that are in the 100 to 1,000 node range.
Yeah. Well, Jean-Pierre, this is very exciting, and I'd like to thank you once again for coming on the show today.
Thank you very much, Rich. Looking forward to seeing you again.
Okay. Yes. Coming up at Frankfurt at ISC for sure. Yeah.
Yeah, I will be there and we'll be showing BXI.
Okay,
sure.
That's a deal. Okay, folks, that's it for the Rich Report. Stay tuned for more news and information on high-performance computing.